Okay, hello everybody. So today we're going to be talking about coupling reactions and NAS reactions as well. So to first start off, I just wanted to talk a little bit about what coupling reactions are. So we're specifically going to be talking about these coupling reactions, and really all they are C coupling reactions. So it's just two carbon bonds coming together, and the reaction is formed by a metal catalyst. So all of these reactions are done with metal ones. So the ones that you're probably going to see most often is going to be Suzuki. They're also all named after people who won Nobel Prizes for them. So that's where the names come from. But I wanted to first start talking about Suzuki coupling. So we're going to go over here. Let me get a text box and write it out. Suzuki. Okay. So Suzuki coupling, all it is it uses a boronic acid. So I'm going to draw out the boronic acid. And this has a lot of applications for a lot of medicines, which can be seen. There we go. Yeah, so Suzuki coupling is probably the most well-known, and it's also probably the most important. There we go. Excuse the bad drawing, but so this is boronic acid, and this is what the molecule that's going to be used to actually do the reaction. So this is going to act as the metal catalyst for Suzuki coupling. And so how it works is I'll go through like one example of how it works, and it's basically just like CC coupling is basically just adding another carbon bond, and it's just attaching the two different elements. So let's say, for example, we have an acetylene ion. Let me draw it better. Okay, there we go. So this is the ion that we're starting with, and we're going to react it with this. I'm going to change colors here. We're going to react it with this ion. So we're going to do plus that. Okay. And so then what's going to happen is you're going to get the same thing, but it's just going to form a double bond. So it's going to go up like that. And instead of this triple bond here, we're not going to have that triple bond anymore. It's going to become a double bond. So there's the double bond. And then you're just going to add on this whole molecule to this part. So it's just going to be like that. And then you'll draw the B. And then, so this is just kind of what it looks like. I'll finish drawing out the molecule here. Okay. There we go. Okay. So this is our first one that you can see. And it is honestly just a pretty good reaction because it is used the most. And so that what happened was this triple bond over here became that double bond. And that is where those two ions are getting attached. So that H comes off and that H comes off. And instead we're replacing it with that double bond right here, which is what you can see. So that's pretty much Suzuki coupling. It's boronic acid, which is what this structure here is. That's boronic acid, and so that's going to be used a lot. So then I'll go ahead and cross this off. We also will talk just kind of briefly about Heck reactions. So we'll put that right there. So then next we'll talk about Sonagashira coupling. And let me type that out. Sure I spelled that right. Okay, so for Sonagashiri coupling, it is going to be using copper iodine. So we'll first write out what it is. So, and it works the same way. It's just joining that carbon bond. It's just attaching two different molecules together, basically, which is all coupling is. These are all just different ways of doing it. So this one is going to use PR2 NH. But the most important part of this reaction is going to be the second part, which is copper iodine and palladium PPH3. Okay, there we go. Okay, so that's what that one looks like, and we'll go through an example. But basically what happens here is we're going to start with an ion that has a halide on it, or an aryl halide, and that is where that group will attach, where this new group coming in with copper iodine is going to attach. So for example, if you have something like this, again, ignore the drawing. So we have an iodine here, and then another one down here. And then we're going to react this molecule with with all of this Sonagashira catalyst. So the catalyst here is going to be copper iodine. So I'm just going to write that one because that one's the most important. And then that just ends up getting attached onto it pretty much. So it would just be like that. Again, fast drawing, we'll just go like that. And then you're going to get this, which is this. So let me finish drawing it and then I'll write what it is. So this gets attached there and is replacing those iodines. So those iodines are reacting and coming off to make this at the end. So that's Sonagashira. We'll go back here and clear this. So put a little thing there. Then we'll talk about Heck reactions, style coupling, and then Nagashi, and then we'll quickly talk about elimination addition and then addition elimination. So those are just the last things that we have to do. So for Heck reactions are a little more complicated because they don't have a transmetallation step. Instead, they use an olefin, and so it just works a little bit differently. It still is coupling in the same way. It just doesn't use metal in it. So we actually won't go over that one because you don't use metal in it, and you don't have a metal catalyst. Instead, you use an olefin. So that one's a little harder to explain. But I did just want to touch on it and show that it is still a coupling reaction. So I'll show a quick example of a Heck reaction. Okay, like that. And then let's say we have iodine. And then something like and then ET just stands for ethyl. Okay, there we go. So that's what we're starting with. So then basically what would happen, your product is just that this part here is going to come off and it's just going to couple with this. So you end up getting something like then you have your O, E, T, and your double bond of oxygen here. So it's just come together and you use palladium 0 for this. That wasn't a very good P. There we go. So this is a Heck reaction. And like I said, we're not going to go over it in more detail because it doesn't use metal. So there's that one. So we'll draw a little check mark again. Okay, so then for style coupling, it uses 10. So it uses SN. So we'll go back over here. We'll use green. Why not? So you, for all of these reactions, you're starting with an aryl halide and then you're using a metal catalyst to form a new compound. So for this one, if you have an aryl halide, like so, and then what I'm about to draw, this is the catalyst that we're going to use. And it's SN, BU, three. And you can just draw the attachments like that. And then you use palladium here as well. But because it's, this is the part that we're focused on, this 10. So palladium is just used as a part of the reaction, but it's not what actually is making the reaction happen. Whereas like in a Heck reaction, the metal, there's no metal in it, so the palladium is doing all the work. So then you end up with a product that's just going to be like Si. And hopefully you can see where all of these like reactions are being added. So this, the 10 comes off and we're going to add that on there. And I'll show it a little bit better too. Okay, so that's going to be our product, but what's reacting here is this part, this little part here, that of that aryl halide is going to be reacting with the 10. So that's what's happening for style coupling or still coupling. I say style, but I don't know what the correct way to pronounce it is. So that's how that one works. These are all pretty simple reactions once you understand that it's just a metal catalyst reacting with an aryl halide. So I'm actually going to write that down right here. So it's just an aryl halide. Again, with the exception of a Heck reaction. That wasn't a very good. I'm just going to type it. Okay, so it's just an aryl halide plus a metal catalyst equals a coupled reaction, pretty much. So that is what that is. And then finally, we're going to talk about Nagashi coupling before we get into our nucleophilic addition substitution reactions. So for Nagashi, we'll come over here. Nagashi is pretty easy to remember because it's the only one that uses zinc. It uses zinc bromide. So for Nagashi, and I forgot to write the other one up here, but let me quickly type it. So you guys can see it. Okay, so for Nagashi coupling, this is the compound that we're going to be using. This is going to be our metal catalyst in this reaction. And it can look a little differently. And once you guys start practicing, you'll be able to do really big molecules that are used in medicines and stuff like that. But for this one, I'll just go ahead and draw out another example. I think it's just helpful to see examples because that's the way that I learn. So we have our zinc bromide there. And I'm just going to draw a circle. There we go. And then we're going to be reacting it with chlorine. And this particular problem also had fluorine in it, but fluorine does not react. Fluorine, it reacts, but it never couples. Fluorine will never couple. So if you ever have a problem like that, just know that it's only going to be this part coupling with this part. And I'm also going to write just what the reaction is here. So this also uses palladium. And it also will be in solution of THF. So then these two parts are going to be the ones that are coming together. So those little yellow dots, those are what's going to be getting drawn. So I'll just draw those out real quick. And then we still have our nitrogen there. And then you're just going to be adding that right where chlorine is. And then you keep your fluorine on there as well. And these are all benzene rings. So there we go. Okay, so that's Nagashi coupling. So basically just a rundown. I'll come back here so I can type this out. So Nagashi is going to be zinc bromide. Then we have still coupling, which is going to be tin. We have HEC, which does not use, it has olefins instead. Sonagashira, which uses, Sonagashira uses copper iodine. And then for Suzuki, which you're going to be seeing the most often, it's that big boronic acid. So that is kind of just a general overview. How do I make it bigger? There we go. So this is just kind of a general overview for what that's going to be. I'll change the color. So there you go. Now you know it's important. So that's what those are. So that's just quick coupling reactions and just going over that. And then quickly, we'll talk about, we'll quickly just talk about NAS reactions. So we'll first start with NAS1, which is elimination addition. So for this one, I'm just going to go ahead and draw out a problem because I think it's easiest to just see it that way. And then we'll quickly also talk about NAS2. And NAS stands for nucleophilic aromatic substitution. Yeah. So we'll go ahead and I'll show you that. So this is NAS 1. Okay, there we go. So I'll go ahead and draw. I think that these are also genuinely pretty like easy reactions because you're just reacting a nucleophile. So it's not too bad. And then you have hydrogen here. And then you're going to be reacting with NH2. So first step here. So an NH2 is a nucleophile because it has these lone pairs here. So first, you start by attacking the hydrogen. That hydrogen is going to break that bond and form another double bond outside. So that gives you that, but then you also have another double bond out here. And you have bromine still there. Boron. No, bromine. I was right. And then you react it again because that NH2 now has 2 sets of lone pairs. So it's going to react again. And it breaks the double bonds. So then that breaking that double bond attaches NH2 on there. And then now you also have bromine in solution because that kicks that off. So then you end up with just this NH2 ion. So that's why it's called, this one's elimination addition. So you're getting rid, oh, right. Okay, so you're getting rid of this, of the bromine, and you're adding in the NH2. So that's that first reaction. And then for NaS2, it's the same thing, but instead it's addition elimination. So you add something on first, and then you end up with something else. So it's not, it's just a little bit backwards, if you want to think about it like that. So we're going to start the benzene ring, probably the best benzene ring I drew the entire video. Sorry about that. And then you have NO2. That wasn't exactly on there, but that, you know, you get the point. Okay. And I'm just going to write it out. Okay, there we go. Make it a little bit faster. And on that O, it has those lone pairs, right? Hopefully you can see those. Okay. So what happens is it reacts like that. That comes out, and then it creates this whole substitution thing. So the first step, you get fluorine and this OCH3. And you still have your NO2 down here, but I'm just not gonna write it right now. And then there are 2 lone pairs right here that are gonna react down here. And then those come down there. So then you end up, and it goes through this whole process of like electron rearrangement basically, but then you end up with, so this is the addition step. So we'll get there in a minute. I'll finish the reaction. So you end up getting this. That was really bad. So your NO2 stays on there the whole time. And then CH. 3. Okay. So this is the addition part. You're adding in the OCH3 there. And then the elimination part is also in this area when you're getting rid of the fluorine, because eventually through all this electron movement, it kicks off the fluorine. So you just end up getting this compound. So that's how those both work. So we've covered all the things that we need to cover. Yeah, so if you have any more questions, check out more YouTube videos, like and subscribe.